yeah, so our paper is called Nondeterministic Situation Calculus. It's joint work with Giuseppe de Giacomo and myself. Basically, probably most of you know the situation calculus, and you know that in the standard version.
Audio is quite bad.
Okay. Atomic actions are deterministic. The situation that results from doing an action is denoted by a term, actually this should be do AS, and this denotes a unique situation in each model. So you can see that the way the situation calculus is set up is really made for determinism. But of course, there are many applications where actions have more than one possible outcome. So we want to accommodate these kind of non-deterministic action. Examples are flipping a coin or trying to stack a block where the block may fall down on the table, or the action may be successful. Or so there's been many previous approaches to doing that. For example, non-deterministic ConGolog program. But most are rather cumbersome. You have to specify a lot of things. And many of them have a problem where they don't really distinguish clearly between what the agent chooses and what the environment chooses. So we wanted to address this. So essentially develop a simple extension of the standard situation calculus that accommodates these actions. And our approach kind of has some nice properties. It preserves the solution to the frame problem due to writer, and also one can still do regression and answer projection queries through regression. And in the paper, well, we show how we can handle font planning as well as the executions of ConGolog program in non-deterministic domains. So let me try to sort of go over this in the limited amount of time I have. So what's the idea of our approach? It's basically that when you have a non-deterministic action, the outcome is determined by what action the agent performed, and also what the environment reaction to that agent action is. And so the way we handle this technically is to say that every action function, action type, besides the normal parameters of the action, like pick up a block, it would take an environment reaction E as an additional parameter. So basically, the full action that includes the environment reaction, we call this a system action. And then what the agent does is he performs the reaction suppressed version of the action. So he doesn't choose the environment reaction. So having this approach allows us to quantify separately over the agent action and the environment reaction. And so we define basically what we call non-deterministic basic action theory, so NDBAT, which is kind of an extension of, or a special kind of BAT, okay? So, an NDBAT is a BAT where first every action function has one of these environment reaction parameters. There's, for every agent action, there's a formula that specifies when the agent can perform the action, okay? We call this POS AG. And this is distinct from the system action being possible. And then there's two requirements for how the reaction connects to the agent action. So basically, we say that whether the agent, whatever environment reaction is, the action by the agent, if the system action was possible, then the agent action must have been possible. Okay, so if the agent can do it, the environment cannot prevent him from doing it. And yeah, well, that's actually the second requirement, the reaction existence. So if the action is possible for the agent, then there must be some reaction that the agent can do. So it cannot basically prevent the agent from doing it. But whether the agent can do it is independent of what the environment might do. Okay, and so these requirements must be entailed by the action theory to have an NDBAT. As usual, so you have action precondition axiom for the system action, and these essentially specify what environment reactions are possible. So this might depend on the context. Okay. The successive state axioms specify how fluents are affected by the system action. So this includes the reaction. And you have initial state axiom and unique named axiom for action as usual. So let's look at the very, very simple example. So here, imagine an agent that can move back and forth along a track, and where we have two actions forward. This actually can move the agent forward by 1 or 2 positions. Okay, so it's non-deterministic. And then we have a deterministic action back by 1 that goes back by 1 position. So the way you would specify this is to say that, this is the precondition for the agent action. So you can always go forward. You can go backward by 1 if the position is greater than 0. And then here we specify which environment reactions are possible for forward. So here we can see that the reaction can be essentially moved by 1 or moved by 2. Okay, and the successive state axiom says that the position of the agent after the forward action depend on what the environment reaction was. He moved by the associated number of steps. Okay. Okay, so this is the basic framework, and now to make this useful to talk about, agent possible agent behavior, so we need to define various notions. So we define a predicate do that says that given a sequence of agent actions, which situation can you reach if you start in situation S? Okay, and these are obtained essentially by existentially quantifying over the possible environment reaction. Okay, so we'll see an example shortly. So this is essentially defined inductively over in terms of do, the big do. Okay, we also have other definitions. So certainly after, so phi is certainly true after sequence of action sigma in situation S hold if for every situation that can be reached after doing this action sequence phi hold. Possibly, it means there exists one. Okay, and we also have notions of a sequence is certainly executable. So in every possible, at every step of every possible outcome, you can do it, or it might be just possibly executed. So the executable, depending on what outcome you get. So one interesting result is that all of these are equivalent to regressible formulas. So basically you can use regression to answer projection queries. So to see how this applies to our example, so we can see that if the agent does, he's starting at position 0, so if he does forward, he might move to 1 or 2, and then goes back by 1, then possibly he's in position 0 after this, or possibly he's in position 1. If he does forward and then back twice, then certainly he's in position 0. In the only situation that can be reached, he's in position 0, but the second back 1 may not be executable if he went forward by only 1 the first time. So this sequence is not certainly executable. Okay, so in terms of, as I said, we looked at how you can handle font planning and synthesis in this kind of framework. So basically, we define in the paper how you can translate an arbitrary font domain specification expressed in a kind of first order version of PDBL can be translated into an NDBAT. And then we define a predicate that says essentially that so if the agent is in situation F, he can force a goal to become true no matter what the environment reactions are by performing strategy F. A strategy is a function from a situation to an agent action. So it chooses what the agent does, but not what the environment does. So this is essentially defined as a sort of inductively. Yeah, I don't think I have time to go over the detail. And then we can prove that, if you have a font domain DOM and you get the corresponding NDBAT, then if you have a plan that a strong plan to achieve a goal in a domain, then it's also a strategy such that you can prove that the agent can force the goal to become true by following this strategy in the initial situation, in the associated NDBAT, and vice versa. So if you have such a strategy where this holds, then it's also a strong plan to achieve goal in the domain. And we also looked at ConGolog program execution, because in ConGolog programs you have non-determinism, but we want to say that the non-determinism there is angelic. The agent chooses how to execute the program, okay? But of course, he doesn't control the environment reaction. So these programs include agent action, but not environment reaction. And so we essentially define a notion of the agent can force a successful execution of the program delta starting in situation F by following a strategy which chooses which actions to do. And yeah, so I don't have time to go into the detail, but please look at the paper. Here's a little example. So suppose we have the program that says either do forward or back by 0 more times until your position is a particular destination. So here we can prove that in our domain, the agent can force, there's a strategy for the agent to force this program to successfully terminate, essentially keep going forward until you either reach the destination and then you can stop, or if you're ahead of the destination, you can just go back by 1 and you'll be at the destination. Okay, so that's pretty much, I think that's all the time I have. I don't know if I have time for questions.